Module 3, Lesson 3. This part of the lesson, I'm going to discuss mean and variance, which are mathematical concepts here. Well, let's begin with an example that we have seen twice so far in this module, and that is we toss a fair six-sided die. But not just one time, we toss it many times, and we record the number of dots on the face landing up each time we toss the die. Well, the question is, in the long run, what would the mean or average of the values be? Well, so for example, suppose we have this. So you can see how many are here. Here's 6, another 6. We have 36. What's the mean? Well, we know how to calculate the average. Say you just add up all the values and divide by the total number of values. In this collection, if you look at the pattern, you notice we have 1, 2, 3, 4, 5, 6 ones. And then we have 1, 2, 3, 4, 5, 6 twos. We have 1, 2, 3, 4, 5, 6 threes. We have 1, 2, 3, 4, 5, 6 fours. We have 1, 2, 3, 4, 5, 6 fives. Well, and there's 36 total numbers, so that means we must also have 6 sixes, and you can check this. So the mean, we would just add up all 36 numbers and divide by 36. Well, I can rewrite this as follows. You notice I can write this as 1 times, well, 6 over 36, which is 1 over 6. And then we have plus 2 times, once again, 6 over 36, which is 1 over 6, plus 3 times 6 over 36, which is 1/6, and this continues. If we add this up, we get 3.5. Well, of course, this is not an outcome, but it's an average. Now, this is a very special collection of 36 because I had exactly 6 of each of the possible outcomes. In reality, for a fair die, we would only expect 1/6 of the values to be for any given number in the long run. The other thing I want to say, this mean is a weighted average. Well, what do we see? You notice it's the average of the possible values of capital X, the possible values being 1 through 6, and then weighted with their respective probabilities. In fact, that leads to the definition of expected value or mean. To be clear, this mean that I have calculated, well, we calculated the mean of a sample, but the sample was chosen to motivate the definition of mean for a random variable. So in this lesson, we will discuss mean and variance for random variables. Here's a definition. The mean or expected value of a random variable x is denoted E of x. Now, I'm going to start this video by discussing the discrete case, and we'll do some examples, and then we'll move to the continuous random variable case. So if you have a discrete random variable with support S, means S is either a finite set or a countably infinite set, and we have probability mass function f of x, then the expected value, we add overall x and s. Well, you take x, that's each value in the support times, this is the weighting, the probability. It's exactly what we saw in the last example, and this is how you calculate expected value or mean of a discrete random variable. Now, notation that is very often used, we will use mu sub x to be this expected value. Okay, here's an example. Suppose we are given the types of nucleotides in a DNA sequence have 30% adenine, 30% thymine, 20% cytosine, and 20% guanine. And some algorithm assigns a score 0, 1, 2, or 3 to the different 4 types respectively. And we define a random variable, capital X, to be the score of a randomly selected nucleotide base. Well, we can write a probability mass function right here. So 0 has probability 0.3. This is adenine. 1 has probability 0.3. 2 has probability 0.2, and 3 has probability 0.2. So then to calculate the mean or expected value, maybe I'll use this notation, we just add. So here we're going to have 0 times 0.3 plus 1 times 0.3 plus 2 times 0.2, and then plus 3 times 0.2. Well, what is this? We have 0.3 plus 0.4 plus 0.6, and so we get 1.3. This is the mean or expected value for this random variable, capital X. Wonderful. Here's a definition. It's really just terminology because we're going to be using it when we calculate variance, when we calculate linear transformation of random variables. So if you have some probability mass function for a random variable, and say your support is S, you can talk about the expected value of another function defined on S. And you see it here. So what this is E of U of X. You just add up the sum. Instead of multiplying X times F of X, you multiply U of X times F of X. Now let's just do an example where I calculate the expected value of 2 and the expected value of 2 times X. And I'm using the exact same example on the last page. Okay. Well, the expected value of 2, we take 2 times, so this is the function, each probability. So 2 times 0.3 plus 2 times 0.3 plus 2 times 0.2, 2 times 0.2. Now I'm going to do something here because this is something more general, not just for this random variable and not just for this constant. You notice I can factor out a 2, and then I just have, well, I'll write it, but this is just the sum of f of x over x and s. And we know because this is a probability mass function, this sum right here is just 1. So we get 2. Okay, here's our first answer. Next one, we want the expected value of 2x. Well, here my function is 2x. So we have 2 times 0, which is 0. We have 2 times 1, which is 2. 2 times 2 is 4. And 2 times 3 is 6. Similar to the one above, I could just factor a 2 out of this, and I would see it's 2 times the expected value of x. But maybe I'll just write out the terms. So 0.6 plus 0.8 plus 1.2. You notice this is 2.6. And if you go back and look at the expected value we calculated, it was 1.3. So maybe I'll make this remark now because it will come up when we do linear transformation later in this lesson. Always, the expected value of b is b, where here b is a constant. And if you had the expected value of, say, a times x, this would be a times the expected value of x, where a is a constant. This is true really for any X. Even though I haven't talked about the continuous case yet, it is also true in that case. But for now, it's just a remark based on this example. Okay, wonderful. So some terminology here. Distribution of a random variable. Well, it's not the same as a random variable. The distribution specifies the long run pattern of values, say repeatedly evaluating your random variable. Now, the mean is a measure of a central location of the distribution. There's another important measure which gives you information about the shape of a distribution, and that's called the variance. It measures the spread of the distribution. So let's talk about variance now in the discrete random variable case. All right, let's consider a discrete random variable x, support s. This means either finite or countably infinite, and a probability mass function f of x. Well, we're looking at this function where you take the difference between x and the mean and square it, or the distance between the x and the mean and square it. This is what this function is. If you look at the expected value of this function, this is called the variance. So what you're doing, you could take x minus the mean squared times f of x. This is the variance denoted here, either variance of x or very common sigma squared. Now, it's just a little algebra to see that you could also calculate it this way, and this is easier to work with. So I consider this to be a little shortcut for variance. You take the expected value of x squared and then just subtract off the square of the mean. The final thing I'll mention before we do an example is the standard deviation. Standard deviation is defined to be the square root of the variance. Okay, so here I have two different probability mass functions. You can see the support of capital X is 3, 4, 5. The support of capital Y is 1, 2, 6, 8. For each one of these random variables, we will calculate mean, variance, standard deviation. But first, let's do this for X. Okay, this is a nice exercise in the definitions. Mu sub X. We take 3 times 0.3 plus 4 times 0.4 plus 5 times 0.3. If you add all of this up, we have 4. Maybe I'll underline it. Now, I'm going to use, as I mentioned, this variance. First, let's calculate e of x squared, and then we will have variance, and we can immediately take the square root and get standard deviation. So here I just need to square 3, and then square 4, and then square 5. When I add these up, I get 16.6. Oh, don't underline it yet. That is not a variance. Now comes our variance, sigma x squared. We take 16.6 minus the mean squared, which is 16. So we get 0.6. This one I can underline. And finally, the standard deviation, we take the square root of the variance. And this is approximately 0.775. All right, now let's do the exact same thing, but we're going to work with random variable y. So for the mean, well, here we have 1 times 0.4 plus 2 times 0.1 plus 6 times 0.3, and we have 8 times 0.2. If we add this up, we get 4 again. Okay, x and y have the exact same mean. However, they will not have the same variance or the same standard deviation for that matter. So let's calculate e of y squared. So here I need to square each value of y. 1 squared times 0.4 plus 2 squared times 0.1 plus 6 squared times 0.3 and then 8 squared times 0.2. Here I get 24.4. Now, once again, don't underline it. Here now we're ready to calculate sigma y squared. This is our variance. Well, we take e of y squared minus the square of the mean. You notice, what do I get? 8.4. Finally, the standard deviation of y, well, we take a square root of 8.4, and this is approximately 2.898. 2.898. Now, if we think about what we're looking at here, two different random variables, same mean, but you notice the standard deviation for y is much larger, and this makes sense because of the values of y versus the values of x. The values y can attain are more spread out, and so if you sampled a lot from this random variable, you would expect more of a spread in what you see than if you sampled a lot from random variable x. Very nice. Now, so far, our definitions and examples have been from discrete random variables. The support S is finite or countably infinite. We've talked about mean, expected value, variance, and standard deviation. And what we have seen is all of these are calculated using a sum. We are working with a discrete random variable. Probabilities are calculated with sums, and also means, variances. Well, a standard deviation is a square root, so, but it's a square root of a sum. Very nice. Now for continuous random variables, now x is continuous. We have probability density function f of x. Well, you notice it looks similar for mean or expected value of x. The only thing that changes is instead of a sum, we are integrating. And I have written the integral minus infinity to infinity x times f of x. However, my note is quite important. So if s is the support of random variable x, really to calculate the mean, which is expected value of x, we can just integrate over x and s of x times f of x. This is often more ideal because you don't have to do an improper integral, and especially if you're working with R, in which R is doing numerical integration, entering it this way, well, it will give you a bit more precise of a mean, say. Now, variance, well, you see it looks just like the variance in the discrete case, except we are integrating. And maybe I will just mention also, you can integrate over x and s of x minus the mean squared f of x dx. Or here, our shortcut also remains. You take expected value of x squared minus the mean squared. In fact, this part of our shortcut, this is really the same for both. The only difference is how you calculate mean and how you calculate expected value of some function changes. We are integrating here rather than summing. Once again, standard deviation is the square root of the variance. Now, just as a remark, one reason we look at standard deviation rather than variance itself is that x and the standard deviation have the same units, whereas x and the variance do not. So that's just a remark. Okay, so here I will end this video with this example. It's kind of a review of some things, and then also we can practice the new things. So I like this example. First, we're given a PDF and an interval, but we want to verify we have a PDF. We want to calculate a probability using the PDF, and then the new part, we will calculate the mean and variance. Now, could you do this in R? You can integrate in R, but I think for the purposes of this video, and because my function is just 3x squared, I will just use the fundamental theorem of calculus when I integrate in all three of these examples. Okay, letter A. This is a nice review of the last lesson. How do we show this function is a probability density function? Well, we have two properties. So property one, we need the function to be non-negative on our interval. And 3x squared, well, 3x squared is always non-negative, but certainly it's non-negative on 0 to 1. Okay. The second thing we need to verify that we have a probability density function is the interval needs to be 1. And here we would integrate 0 to 1. We integrate over S in general. All right, well, I mentioned I'm not going to use R. An antiderivative here is x cubed. And then we evaluate between 0 and 1. We have 1 cubed minus, 0 cubed, which is just 1. So property 1, property 2. Very nice. We have finished letter A. Letter B, we want the probability that x is bigger than or equal to 1/2. Well, this is an integral from 1/2 to 1 of 3x squared dx. Once again, I will just integrate. You could use R, but it's not needed here. We have 1 cubed minus 1/2 cubed. This is 1 minus an 8, which is 7 over 8. A and B were a review of really the last two lessons. Now, mean and variance, this is what's new in this lesson. So letter C, the mean, well, we integrate over 0 to 1 of x times f of x dx. Well, I get 3x cubed. Once again, we can just use the power rule. Or you can use R. Here we get 3/4 minus 0, but I will just leave it like this. Last one. You see, I'm going to do this in two parts. Oh, it's still letter C. Okay, well, first let's calculate the expected value of x squared. This will be an integral from 0 to 1 of x squared times 3x squared dx, which is an integral from 0 to 1 of 3x to the 4th dx. We have 3 over 5, x to the 5th, which is 3 over 5. This means that the variance, well, we take the expected value of x squared minus, we need to square the mean here. This would be 9 over 16. And if you take this difference, we get 0.0375. This is the variance. Of course, the square root of this would be the standard deviation. Well, at this point, we can move to the next pages and practice calculating mean and variance in R. Thank you, students.